Welcome to the fascinating world of calorimetry. Calorimetry is the science of measuring the quantity of heat exchanged in physical and chemical processes. It helps us understand how energy moves between objects, especially when they are at different temperatures. This concept is crucial in physics, chemistry, and even everyday life, from cooking to climate science. In this video, we'll explore the basics of heat, temperature, and the unique properties of water that make it so important in thermal phenomena. Let's start by understanding what internal energy is and how it relates to heat. Every molecule in a substance possesses both potential and kinetic energy. The sum of these energies is called internal energy. When you consider all the molecules in a substance, their combined internal energy is referred to as the substance's thermal energy. This energy determines how hot or cold an object feels. For example, a hot object has more internal energy than a cold one of the same kind. When two objects at different temperatures come into contact, energy naturally flows from the hotter object to the colder one until equilibrium is reached. Heat is a form of energy that flows from a hot body to a cold body when they are in contact. It's not a substance, but rather a transfer of energy due to temperature difference. The study and measurement of this energy transfer is what we call calorimetry. Understanding heat flow is essential in many scientific and engineering applications, from designing engines to understanding weather patterns. Let's look at how we measure heat and the units used. To quantify heat, we use specific units. The SI unit of heat is the joule J, but another common unit is the calorie. 1 calorie is defined as the amount of heat required to raise the temperature of 1 gram of water by 1 degree C. In terms of conversion, 1 calorie equals 4.2 joules. These units help scientists and engineers communicate and calculate energy changes in various systems, whether it's in a laboratory experiment or a real-world application. Temperature is a measure of how hot or cold an object is. It reflects the thermal state of a body and determines the direction of heat flow when two bodies are in contact. The SI unit for temperature is Kelvin K, but degrees Celsius degrees C is also widely used. The relationship between them is simple. Tk equals T degrees C plus 273. Temperature is a key concept in calorimetry, as it helps us predict and measure energy transfer. The amount of heat energy absorbed by a body to increase its temperature depends on three main factors: the mass of the body, the rise in temperature, and the material or substance of the body. Experimentally, it's observed that heat absorbed is directly proportional to both the mass and the temperature increase. Additionally, the nature of the substance, expressed as its specific heat capacity, plays a crucial role. Let's break down these relationships further. The relationship between heat absorbed, mass, temperature change, and specific heat capacity is given by the formula Q equals Cm delta. Here, Q is the heat absorbed, C is the specific heat capacity, M is the mass, and delta is the change in temperature. The specific heat capacity is a property unique to each substance and determines how much heat is needed to raise the temperature of a unit mass by 1 degree Celsius or Kelvin. Heat capacity and specific heat capacity are related but distinct concepts. Heat capacity, C, is the amount of heat required to raise the temperature of an entire body by 1 degree C. Its SI unit is Jk. Specific heat capacity, C, is the amount of heat required to raise the temperature of 1 unit mass of a substance by 1 degree C, with SI unit J/kgk. The relationship is heat capacity equals mass times specific heat capacity. Water, for example, has a high specific heat capacity of 4200 J/kgk. Different substances heat up at different rates because of their specific heat capacities. If you heat equal masses of two substances with the same amount of energy, their temperature rises will differ. Substances with low specific heat capacity heat up quickly, while those with high specific heat, like water, heat up slowly. This property makes water an excellent heat buffer in nature and technology. A calorimeter is a scientific instrument used to measure the amount of heat gained or lost by a body. It is essential in experiments involving heat transfer, such as determining the specific heat of substances or studying chemical reactions. The principle behind the calorimeter is based on the law of conservation of energy. The heat lost by a hot object is equal to the heat gained by a cold object. The method of mixtures, or the principle of calorimetry, states that the heat energy lost by a hot body is equal to the heat energy gained by a cold body, assuming no heat is lost to the surroundings. Mathematically, this is expressed as M1C1 delta equals M to C to delta, where M and C represent the mass and specific heat capacity of the two bodies, and delta is the temperature change. This principle is fundamental for accurate heat measurements. Water has an unusually high specific heat capacity of 4200 J/kgk. This means it can absorb or release a large amount of heat with only a small change in temperature. This property has significant effects on our environment and daily life, from moderating climate to making water an effective coolant in machines. Let's explore some real-world consequences of water's high specific heat. One major consequence of water's high specific heat is the moderate climate near seashores. Water heats up and cools down much more slowly than land. For the same amount of heat, water's temperature rises about 5 times less than sand. This means coastal areas experience less extreme temperatures, making the climate more comfortable for people and wildlife. Hot water bottles are commonly used for fomentation or applying heat to the body. Thanks to water's high specific heat, these bottles retain heat for a long time and release it gradually. This makes them effective for soothing aches and pains as they provide warmth over an extended period without cooling down quickly. Water's high specific heat makes it an excellent coolant. In machines like car engines and generators, water flows through pipes around heated parts, absorbing heat and preventing overheating. Because water can absorb a lot of heat without a significant temperature rise, it efficiently removes excess energy and keeps machinery running safely. In cold countries, water is often used as a heat reservoir for wine and juice bottles to prevent freezing. Because of its high specific heat, water can give off a large amount of heat before it itself freezes. This property helps protect delicate liquids from freezing even when temperatures drop below zero. Farmers use water to protect crops from frost on cold nights. When temperatures drop below freezing, water in plant veins can freeze and expand, damaging the plants. By flooding fields with water, farmers take advantage of water's high specific heat, which helps keep the temperature above freezing and saves crops from frost damage. All plants and animals contain a high percentage of water, about 80 to 90%. This water helps maintain a stable body temperature in all seasons, thanks to its high specific heat. It acts as a buffer, absorbing and releasing heat slowly, which is vital for survival in changing environments. Objects with high heat capacity, like thick cooking pans or heavy electric press bases, heat up slowly and retain heat longer. This is useful for cooking and ironing, as it ensures even heating and keeps food or clothes warm. On the other hand, calorimeters are made from thin copper sheets with low specific heat, so they quickly match the temperature of their contents without absorbing much heat themselves. A change of phase occurs when a substance changes from one state to another, solid, liquid, or gas at a constant temperature. This process is driven by the exchange of heat. Melting, freezing, vaporization, condensation, sublimation, and solidification are all examples of phase changes. Each involves either the absorption or release of heat energy. The melting point is the constant temperature at which a solid turns into a liquid, while the freezing point is where a liquid becomes a solid. Most substances expand when they melt, but some, like ice, actually contract. The presence of impurities can lower the melting point, which is why adding salt to ice makes it melt at a lower temperature. The heating curve of ice shows how temperature changes as heat is added. When you plot temperature against time, you see that ice first warms up, then melts at a constant temperature, and finally the resulting water heats up further. The flat part of the curve represents the phase change, where heat is absorbed but temperature stays the same. Pressure can affect the melting point of substances. For materials like ice that contract on melting, increasing pressure lowers the melting point. For substances that expand on melting, like wax or lead, increasing pressure raises the melting point. This principle is used in various industrial and natural processes. Adding impurities to a substance affects its melting and boiling points. Impurities lower the melting point and raise the boiling point. For example, adding salt to ice lowers its melting point, which is why salt is used to melt ice on roads. Similarly, adding salt to water raises its boiling point, making cooking faster and more efficient. Vaporization is the process where a liquid turns into a gas at a constant temperature known as the boiling point. When a liquid boils, it absorbs heat, but its temperature remains constant until all the liquid has turned into vapor. The boiling point can be affected by pressure and impurities, as we've seen earlier. The heating curve for water illustrates how temperature changes as heat is added. Starting at room temperature, water heats up until it reaches its boiling point. At this stage, even though heat continues to be absorbed, the temperature remains constant as the water turns into steam. This flat section of the curve represents the phase change from liquid to gas. When water boils, its volume increases dramatically. For example, 1 cm3 of water at 100 degrees C becomes about 1760 cm3 of steam at the same temperature. This expansion is why steam engines and pressure cookers work so effectively, harnessing the power of expanding steam. Latent heat is the energy absorbed or released during a phase change without a change in temperature. When expressed per unit mass, it's called specific latent heat, denoted by L. The formula is L equals Qm, where Q is the heat absorbed or released and m is the mass. This concept explains why temperature remains constant during melting or boiling. The specific latent heat of fusion of ice is the amount of heat required to melt 1 unit mass of ice at 0 degrees C to water at 0 degrees C without any change in temperature. Conversely, it's also the heat released when water at 0 degrees C freezes to ice. This property is crucial in understanding natural phenomena like snow melting and the cooling effect of ice. According to the kinetic model, molecules in a solid vibrate about fixed positions. When a solid melts, the average kinetic energy doesn't change, but the separation between molecules increases, requiring energy to overcome attractive forces. This energy goes into increasing potential energy, not temperature, and is called latent heat of melting. This explains why temperature stays constant during melting. The high specific latent heat of fusion of ice leads to several important natural effects. Snow on mountains melts slowly, lakes and ponds in cold regions freeze gradually, and drinks cool faster with ice than with cold water. When ice melts in a frozen lake, it absorbs heat from the surroundings, making the air colder. This is also why it feels colder after a hailstorm.